Hello everyone. In this video, I'm going to be taking a look at some power series examples, and specifically in which I'm going to be I'll look at some expressions involving multiple series, and we're going to be combining those into a single series, an expression with a single infinite series, through the use of reindexing. And hopefully, you'll see what I mean by that when we get into the. I have 3 examples for you. Now I have to preface this video by saying that this is a video that's made for an introductory differential equations course. So I am assuming that if you're watching this, that you have taken some sort of calculus series, calculus 2, calculus 3 course where you were introduced to power series and all that. So I'm not this isn't going to go that deep into power series as you would see in a calculus 2 course. Okay. So my instructions for this first example and every example for the rest of the video is going to be rewrite the given expression using a single power series whose general term involves x to the k power. All right, so for right now, I have the sum from n equals 1 to infinity of n times, some constant c sub n times x to the n minus first power. All right, so here the general term involves x to the n minus 1 minus, and then the infinite series, from n equals 0 to infinity of c sub n, right, that's a constant c sub n, times x to the nth power. Right, so the general term for this series involves x to the nth. So what I'm going to be doing, and this is really in practice for some skill. This is a skill that's going to be necessary when attempting to solve a differential equation using power series to find a power series solution for some differential equation. So right now my index variables, the indices, are n, right? And the thing that's changing, right, that's the index. And what I'm going to do is I'm going to re-index to the point where eventually I have, my index will be, I'll call it k, and I'll have the expression rewritten so that there's a single series involving x to the k. Alright, so the important thing here before re-indexing is to possibly pull some terms out of the sums so that every series starts with the same power of x. Right. So I'll make that note off to the side here. So before re-indexing, going to manipulate the expression so each series in the expression starts with the same power of x. So I'll just say get each series to start with the same power of x. Or the same power of whatever the variable is. The independent variable, right? It doesn't have to be x all the time. So if you look at these two series, this series starts, when n equals 1. So the first term of this series would be 1 times, c1 times x to the 0 power. Right? When n equals 1, you have x to the 0. So this series starts with, in its first term, x to the 0 power, or just a constant. this other series also starts with x to the 0. So this is a very actually easy example because I have it, it's already set up where the series are starting with the same power of x. So now that they have, now that all my series start with the same power of x, I'm going to re-index each series. Meaning the following. Again, just to have a generic, I'm going to have each series have, instead of depending on x to the n minus 1 or x to the nth, I want them to depend on x to the k. So in this series, I'm going to replace n minus 1, this exponent on the variable, replace it with k. Or think about this as replacing all the n's with k plus 1. And let's see what that series will look like. So I'd have the sum from, now if n equals 1, then, and we're re-indexing to have an index of k, when n equals 1, k would be 0. Right, so it would start off with k equals 0 to infinity, right, because as n approaches infinity, k would approach infinity as well. And then n again is the quantity k plus 1 times c sub n, right, so times c sub k plus 1, and then times x to the n minus 1 or x to the k. Okay, and these really are, again, just because they have a different letter now, k instead of n, they are the same series. And you can see that by just looking at the first several terms. They have the same exact terms. Right? When k equals 0, you get 1 times c sub 1 times x to the 0, exactly the same term that starts off this series when n equals 1. Right? And so on. You could check other terms. But these are the exact same series, just re-indexed. Right? Now instead of the index of n, you have an index of k. Okay, and then basically like you're starting a whole new problem, even though it is part of the same expression. This series here, do the same thing. Just to get it to have the same index variable as the other series. Instead of x to the nth, I want x to the k. So I'm going to let k replace n, right, in this second series. And let's see what we get. We get the sum. Now, basically it's just the same series, but k replaces n. So from k equals 0 to infinity of c sub k times x to the k. Alright, now it's still not a single power series yet, right? I have two power series, but now that I have two series with the same index, and they both have the same initial, the starting value, right? Same initial index value, same starting value if you want to call it that, then I can combine them. All right, then I can combine them to make a single sum, or an expression with a single power series. So in combining these, we'd have, this is equal to the sum, from that k equals 0 to infinity of, and then this minus this. And again, notice how both of these have x to the k in common. I'll factor that out. So we'd have a k plus 1 times c sub k plus 1 minus c sub k times x to the k. And there we have it, right? Here is our original series, our original expression with the two series written as an expression with a single power series, right? One sigma notation. And they really do represent the same expression. These are the same, and you can test this out by writing out, the first 5 terms of this, write out the first several terms of these, and you'll see that and combine some like terms, and you will see that they are indeed the same. Okay. So again, this is going to be an important skill for when we are finding power series solutions of differential equations. Okay, so let's do this again. So my next example, same instructions. Right, rewrite the given expression using a single power series whose general term involves, x to some power, x to the kth power. Again, it doesn't have to be k. You can make it whatever index variable you wish. I'm just using k. Right. All right, so again, I have this expression with, the sum of 2 sums, right? Just a large sum that I would like to rewrite so that there's a single sigma, a single summation notation, single power series. All right, so as before, first off, my indices, they're the same variable. They're both this n, but they don't start at the same value, and so I want to change that up. And also, before I re-index with the k, I'd like to, manipulate this expression so that all the series in the expression start with the same power of x. All right, so if you look at this first series, when n equals 1, you have 2 times 1 times some constant c1 times x to the 0. All right, so this series starts with x to the 0 again. All right, now here's I threw out hopefully more and more. The 3 examples I've chosen get slowly more complicated. This series, when n equals 0, starts with 6 times some constant c0 times x to the 0 plus 1, x to the first. So this series, if you were to write out, the first term, starts with x to the first power. All right, so these are not starting with the same power of x. But in order to do the proper re-indexing and get a single series in here, a single summation in this expression, I want to make sure the series start with the same power of x. Alright, so just take the lower ones, right? This series starts with a lower power of x, and just basically write out terms, take out terms from that series until you get to a series in this expression that starts with the same power as x as the higher one. Here's what I mean. So if I pull out, say, the first term, when n equals 1, so this series here, so I start writing out terms. When n equals 1, I'd have 2 times c1 times, x to the 0. But there's no reason to write x to the 0, right? That's as long as x is not the number 0, that would be 1. Right? Anything to the 0, any non-zero number to the 0 power would be 1. All right, plus, and then, now the summation would look like this. Because I pulled out the term when n equals 1, the summation is now starting at n equals 2. Right, so from n equals 2 to infinity of, and then the same look, right? 2 times n times c sub n times x to the n minus 1. And now this series, starting at n equals 2, this series starts with x to the first. And that's exactly what I want. All right. I want all, so and this series already starts with x to the first. So I'm going to leave it the way it is. The sum from n equals 0 to infinity of 6 times c sub n times x to the n plus 1. Right, now all the series. Now I have this 2c1 out here. That's going to stay there. Right, any terms I pull away from a series is going to stay in the expression. All right, so now comes the reindexing. All right, because both series in my expression now start with the same power of x. Now comes the reindexing, where I get, instead of x to the n minus 1 and instead of x to the n plus 1, I'm going to have x to the k power in both of these. So now I'm going to reindex. Alright, so in this first series, instead of, I don't want x to the n minus 1, I want x to the k. So I'm going to let k replace the n minus 1. Or, if you'd like, n be replaced by k plus 1. Right, just adding 1 to both sides here. Well, now the expression looks like this. Sorry, I should be putting equal signs here. So I still have this, again, I have this term I pulled out earlier, this 2c1, that's not going anywhere. Plus, and now this sum after reindexing with k looks like the following. We'd have the sum. Now when n equals 2, k would be equal to 1. Right? So the new lower limit for the index is k equals 1. To infinity, right? Because again, as n goes to infinity, k would go to infinity. Of 2 times n, so 2 times the quantity k plus 1, times c sub n, or c sub k plus 1, times x to the n minus 1, which is, times x to the k. Okay. Plus, and then again, same thing over here. All right, again, imagine you're starting over. It's a totally different series. I want to reindex so that, instead of having terms involving x to the n plus 1, I have terms involving x to the k power. I use the same indexes over here. So I'm going to again replace the power here, n plus 1. I'm going to replace that with k. So I'm going to have k be replacing n plus 1, or n equals k minus 1. Same thing. So now this sum becomes the following. Right, the sum, now it should have, if you did everything correctly, starting the series off with the same power of x, and then do this reindexing, the lower limit on each sum, the lower index value should be the same if you're doing everything right. And that is the case here, right? When n equals 0, k equals 1 is the lower limit. Same lower limit as the other sums, so that means I can put them together. All right, we can put them together as a single sum because they have that same lower limit. K equals 1 to infinity of, and then 6 times c sub n, but n here is k minus 1, times x to the n plus 1, or x to the k. All right, and now finally I can put both these sums together. So this is equivalent to 2 times that c1 plus, and then putting these sums together, we have the sum from k equals 1 to infinity, right? And then both these expressions get added together, and they both have, x to the k in common. So I'll factor that out, right? So we have 2 times k plus 1 times c sub k plus 1, then plus 6 times some constant c sub k minus 1 times x to the k. And there you go. Here's how that expression there is rewritten as an expression with a single sum in it. All right. Yeah, there's this extra term that I pulled out, the 2c1, but still there is only a single power series involved here. and that's what we wanted to get. And again, you can verify this by going back to the original sum and just take the original sum, the original expression, write out a bunch of terms, combine some like terms, then write out a bunch of terms of this expression here, this 2c1 plus this sum, and you'll see that indeed they are the same series. They represent the same stuff. They have the same exact terms. But again, I'll leave that to you to verify. Alright, I just got one more example of this. Same instructions, okay, but it's a little more complicated, this one, because my last example has 3 sums involved, but the setup is the same. All right, the setup is the same. Now all 3 of these sums have a different lower limit for the index, n equals 2, n equals 1, n equals 0, so obviously I cannot combine them right now. They're also dependent. They're also involving different powers of x, which I don't like. If I want to write this as an expression with a single sum involved, a single power series, I'd like the same power of x in every sum and the same lower value for the index. So just like earlier, I want to make sure every single one of these sums starts with the same power of x. Alright, so this first sum starts with x to the 0, right? When n equals 2, your first term would have x to the 0. This second sum starts with x to the first, right? When n equals 1, you got x to the nth here. And this final sum starts with x to the 0. Alright, so the highest of these is x to the first. So that's the one I'm going to leave alone. It's these other two. If I start with x to the 0, in order to get to x to the first, I just need to pull one term out of each of these. Right? So I'm going to rewrite all this here by pulling one term away from this sum, one term away from this third sum, and leaving the second sum alone. Then all the sums that are left over will start with x to the first. Alright, so if I say when n equals 2, this is going to be 2 times 2 minus 1, so 2 times 1 times c2, and then times x to the 0. Alright. So that's the first term pulled out of that. And I'll also pull out the first term of this third sum over here. When n equals 0 over here, we just have c0 x to the 0, so plus c0. Alright, so that's the first term pulled out of this first sum, the first term pulled out of this third sum, and then I'll rewrite the rest. Alright, so I've already pulled out when n equals 2 here, so that the leftover sum will be when n equals 3 to infinity of this, n times n minus 1 times constant cn times x to the n minus 2. This sum I didn't pull anything from, so I'm going to leave it the way it is, minus. Now, just because I'm going to be putting all these together, I'm going to put the 2 inside the sum, right? You can pull constants out, put them in. So I'm going to make that the sum from n equals 1 to infinity of 2 times n times c sub n times x to the nth. All right. And then finally plus, and again I pulled the first term, that was this c sub 0 here. I pulled the first term away when n was equal to 0. So now the sum starts with when n equals 1. So n equals 1 to infinity of, c sub n times x to the nth. All right, now every single one of these series starts with x to the first in their first term. Right? So now that I've got all the series in my expression to start with the same power of x, let's reindex. Make it so that they all involve x to the kth power. Right. So again, for this first sum, I'm going to have k replace n minus 2, or have n be replaced by k plus 2, same thing. In this second sum, I'm simply going to have k replace n. And the same thing for this third sum. I'm simply going to have k replace n. So pretty simple, those last two. Alright, so finally we have, this is equal to, now I'll rewrite this, so we have c sub 0 plus 2c sub 2. C0 and c2 are constants. Plus, then this sum, rewritten with the new index of k, is, k equals 1, right? Because when n equals 3, k equals 1, the new lower limit's 1, to infinity of, and then n is k plus 2, then n minus 1 would just be k plus 1. So it's k plus 2 times k plus 1 times c sub k plus 2, and then times x to the k. And then the second sum, we have minus the sum from k equals 1 to infinity of 2k, right, n equals k here, times c sub k, and then times x to the k. And then final sum, the sum again, just n's replacing k again here, so from k equals 1 to infinity of c sub k, x to the k. And now every single one of these has the same lower limit on this index of k, same lower limit for the summation. They all involve x to the kth power. I can pull that out. And in fact, these last two also involve c to the k. Right? So you're going to see me pull out c to the k from those last two as well. So here's what we end up getting when we write this involving a single summation. So we have that c0 plus 2c2 plus, and then sum from k, k equals 1 to infinity of the following. So I've got, k plus 2, and I'll put it in the other order, k plus 1 times k plus 2 times, some constant c sub k plus 2. Then over here, I'm going to do this. Both of these coefficients of x to the k have c to the k in it, and you have negative 2k plus 1 of those, so I'll have the quantity 1 minus 2k times c sub k. And then all this is coefficients of x to the k. Wonderful. And there it is. This is the original expression, now written as an expression with a single power series in it, right? A single summation notation. And if you'd like, and I'll leave it to you, to see that this truly is equivalent to the original series, the original expression I had. Take that original expression, write out the first several terms of each sum, combine like terms if you need, and Then take this one, write out the first several terms of all this, and you're going to see the more and more terms you go out there that they're all the same. You get the same exact terms in this series, in this expression, as you would in this expression. Right? So that they are indeed equivalent. Okay, and that's it. All right, so you notice I went through the same the same procedure in all three examples. Try to get all your series to start with the same power of x. If you need to pull out some terms from certain series to do that, then do that. Then reindex, right? Just basically go through each series, replace all the powers on the x, all the exponents with some other letter k or j or whatever you want. And if you did all that properly, you should be able to then express the same expression with a single power series. Wonderful. All right, so hopefully watching me go through these three examples help you out when you're doing problems similar to this. And thank you very much for watching.